What is Life by Schrödinger, a resume? Hi, my name is Wani and I'm a philosophy student at La Sorbonne. So this was actually my gateway drug into quantum mechanics and I hope that this is a very fun trip for you as well. This video is going to be divided into 3 parts. The first is non-application and application of statistics in biology. I'll be talking about heat motion, energy threshold mutation, so it's physics parallel with physics. The second, I'm going to be talking about its non-application in terms of the hereditary treasure, biological laws such as meiosis and syngamy. And the third is application, so crossing over and the locus of the gene. The second is the parallels between mutation and quantum theory. So first, I'll explain discontinuity and energy threshold. Secondly, I'll talk about recessive and dominant mutations, phenotype versus genotype. Then I'll explain the quantum jump. And lastly, I'll talk a bit about the living cell in 2 optics, which is essentially what this whole book is about, how it is that you can examine a biological object, which is the chromosome, in terms of an object of physics, which is the aperiodic crystal. It's been a while. I wrote this last semester. Third is going to be from living cell to living system. So here I talk a bit about entropy, ways of producing orderliness, statistical mechanism, order from disorder, entropy, and dynamical mechanisms, order from order, or the energy threshold. Just so you know, I got a 17 out of 20 for this paper, this resume, and he says that it's a good resume that highlights the important aspects, but certain passages would have merited to be more developed. So that's just to give you an idea of how successful this paper was in terms of my professor. But let us begin. What is life? The physical aspect of the living cell, 1944, is written by Nobel Prize winning Austrian physicist Erwin Schrödinger, based on his 1943 public lectures as the director of theoretical physics at Dublin Trinity College. This book is ambitious not only as it seeks to present a fundamental idea which hovers between biology and physics, thus seeking to produce knowledge from the intersection of 2 distinct scientific approaches, but that it was written in view of addressing the lay reader, i.e. those of minimal to zero knowledge of the theories on which these sciences are based. So like me before I read this book, and hopefully it helps people like you as well. To get into this book. Schrödinger's fundamental idea is poised on the question, how can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? The author demonstrates how it is that we can understand the chromosome fiber, the most essential part of a living cell, an object of biology, as an aperiodic crystal through the applications of theoretical knowledge of physics, namely that of statistics. However, the ambitions of the author goes even further, as after addressing the statistical applications of physics that contribute to the identification of the dynamical law that governs the chromosome fiber, he introduces the statistical law that demonstrates how it is that an organism functions within its environment to avoid entropy, that is, the state of death. Composed of 7 chapters, the book is separated into 2 distinct moments. From chapter 1 to 5, the author demonstrates the living cell as a dynamical phenomenon, while the remaining 2 chapters address the living system as a statistical phenomenon. The keynote from the author is one of refinement, and I quote, "You would not expect 2 entirely different mechanisms to bring about the same type of law," end of quote. Said differently, to seriously address the problem of life, the physicist must be attentive to the varying stages in the development of the living phenomenon, and by extension, the different attitudes or mechanisms necessary to accurately address each stage, from the fundamental configuration of a living cell to that of a complex organism. In the end, he asserts, however, that, I quote, "all physical laws are based on statistics," end of quote, which is to say that all contrasts in pattern, dynamical, or statistical add up to the one and same tapestry. So here I'll begin with part 1, but just don't freak out. Like, we're not gonna go really into depth about all these different structures, but it's just to kind of prep you for the next 2 videos that I'm making on Schrödinger. And it's just so that there's like a reference video of what it is that we're talking about when we talk about mutations, quantum jumps, or what is discontinuous. It's just to help you with your library of contextualizing what these words mean. So the first part, In chapters 1 to 5, the author demonstrates how it is that we can understand the living cell as dynamical phenomenon. Said differently, we see how it is that the material carrier of life, or the chromosome fiber, functions and behaves as an aperiodic crystal. With the statistical foundation of physics, the author begins by considering how it is that an organism behaves and functions, and how he might begin to compare his theoretical anticipations with the biological facts. Under the anticipation that the behavior and function of an organism can be explained by physical laws and patterns, the author introduces 3 examples: paramagnetism, Brownian movement and diffusion, and the measurement of weak forces. All examples highlight the influence of rival tendencies, with the common variable being that of the influence of heat motion. Magnetic field versus heat motion, influence of gravity versus heat motion, concentration of molecules versus heat motion, and finally, how lighter substances are less resistant to heat motion. The purpose of demonstrating these statistical laws is twofold. Firstly, it establishes the source of disorder that causes observable irregularities in the behavior and function in a small portion of molecules. Secondly, the introduction of influence of heat motion is necessary if the lay reader is to understand its implications on the configuration and potential reconfiguration of an isomer molecule, as with the chromosome fiber, as it relates to the energy threshold, and by extension, our understanding of the phenomenon that is mutation. The transition between chapter 1 and 2 is stark. And I quote, "The classical physicist's expectation, far from being trivial, is wrong." End of quote. It bears repeating the importance of the attitude of refinement and the retention of contrasting elements at play. In other words, as no exact statistical law can be derived from an incredibly small group of atoms, i.e. within the limits of a single chromosome fiber, theories of classical physics at this stage are inapplicable. In this section, the author highlights the mechanism specific to chromosome fiber that strictly adheres to biological laws, namely meiosis, the division of cells to produce gametes, and syngamy, where 2 gametes or haploid cells, i.e. sperm and egg, become diploid, i.e. a fertilized egg. This hereditary mechanism is the process between meiosis and syngamy, where a fertilized egg inherits its hereditary treasure, i.e. the dowry of 2 complete sets of chromosomes exactly similar to those of its parents' cells. In this way, the chromosome is said to contain the code script, which represents the entire pattern of the individual. This pattern or structure of the chromosome fibers make visible every causal connection between that which is passed down generationally on a molecular level and its observable properties as it manifests in the offspring. It is through this causal connection identified over generations that statistical physics finds its application. Arriving at accuracy over big numbers, statistical law enables us to identify the permanence of a gene, i.e. its durability over generations. The main application of statistics here is on the probability of crossing over, which is when any 2 homologous, I've never pronounced any of these words out loud, like you just read and you write and now you're like, homologous chromosomes, i.e. that carries the same gene, one from each parental source, come in close contact with one another and exchange portions. What is observed is the statistics of linkage, where 2 properties closely situated on the same chromosome remain linked, and inversely, where 2 properties located on opposite ends are separated by crossing over. So really quickly, and it's not really important, but it's just so that you follow along. Essentially, there's 2 chromosomes and then they cross over and then they make a pair, right? And then you get 2 pairs of chromosomes. The statistical linkage is basically when gene A and gene B are really close to each other, the chances of it being cut off when it crosses over is smaller because they're so close together. Whereas if A and B are on the opposite ends of the chromosome, the chances of them separating is higher because they're so far apart. So this is the whole point of statistics of linkage and why it is that it matters if A and B are closer to each other or A and B are further apart, which is something that I obviously could have written in terms of him saying that I could have explained further. The inference of this is that the statistics of linkage enables the mapping of properties or genes. Said differently, statistical law enables us to locate in the chromosome the seat of difference, or the locus of the gene. It is through our capacity to identify this locus of any particular gene that we are able to identify the locus of a mutant gene, which by extension enables us to explain the quantum jump in the gene molecule. That is the aperiodic crystalline nature of the chromosome fiber. My only critique for this is just So because we have this, we're going to infer this. And then after that, we're going to infer that. And just like, who says that all this actually, adds up to something that is the reality? But okay, science. But back to this. In chapter 3, 4, and 5, the author constructs a striking parallel between Hugo de Vries' theory of mutation and quantum theory as it relates to discontinuity and the energy threshold. De Vries describes mutation as jump-like changes observed in a small number of offspring. This discontinuity is observed as there are, and I quote, no intermediate forms between the unchanged and the few changed, end of quote. A phenomenon similarly observed in quantum theory where there are, and I quote, no intermediate energies occurring between two neighboring energy levels, end of quote. A mutation occurs when two copies of the code script are no longer identical, homologous with the same gene, i.e. that there now is a change or difference in one side of the chromosome pair. Through analysis of observations obtained by crossing mutated with non-mutated individuals, it can be said that mutations are, and I quote, inherited as perfectly as the original unchanged characters were, end of quote. In other words, while mutations usually only manifest in a small portion of a single generation, this change, mutation, in the hereditary treasure, and I quote, has to be accounted for in the change in hereditary substance, end of quote. So how is it that some display the mutation and some don't when they all come from the same parents, essentially? To better understand the change in the hereditary substance, the author highlights the statistical pattern of behavior of mutations, and I quote, recessive mutations are more frequent than dominant ones and are very important, though at first they do not show up at all, end of quote. Here we identify the difference between phenotype and genotype. Phenotype is what is visible, the version of the code script of characteristics that manifests in the offspring. Genotype is the two versions, two alleles. You can Google this, but I just don't want us to start thinking that I'm teaching us biology. I just want to teach us the philosophical implications. So that make up chromosomes inherited, again, one from the father and the other from the mother. The genotype is heterozygous when the versions are different from homozygous. I'll write the word somewhere. When the versions are equal. A version is dominant when it is followed and recessive when it's not. Working backwards, as a mutation is recessive, it often does not manifest as the phenotype of an individual. Though it does not manifest, the genotype is changed due to the introduction of the mutation. The genotype having transitioned from the homozygous to heterozygous thus represents the change in the hereditary substance. So the idea is that you can possess it, but because a mutation is recessive, as in it has no tendency to manifest, it means that there is a change in the hereditary substance, but it doesn't mean that you're going to see immediately the changes in terms of appearance. So genotype and phenotype is something that needs to be studied separately, and you need to really pick out the different elements and the different pieces, which is something that Schrödinger does really well in general with his methodology. Again, if this is something that's interesting to you, I'm sure that there are a lot of biologists who can pronounce homozygous and heterozygous correctly that could inform you better on this. So continuing on, this application behind the hereditary mechanism dates back to the distinctions made in early history of genetics, as credited by the author, and I quote, the law of inheritance to successive generations of properties in which the parents differ, and more specifically, the important distinction recessive-dominant, are due to the now world-famous Augustinian Abbot Gregor Mendel, 1822 to 84, end of quote. This is just an academic thing about how it is that was Mendel actually a precursor? So basically, Schrödinger is giving credit to someone who, for the most part during science, in terms of its history, they gave it to 3 other people. But again, now we're going too far. But the important thing to take away from here is, despite whether he is the person who discovered his own thing called the Mendelian or the Mendel ratio, is that he for sure is the first dude who talked about recessive and dominant. And that's the whole point here. So continuing on, a mutation is therefore more frequently recessive, as for it to be dominant, it must be present on both sides of the chromosome pair. Besides the structural changes necessary for a mutation to manifest, the author emphasizes on the necessity of the mutation being a rare event as a form of comparative conservatism, which prevents multiple and simultaneous mutations that would lead to the perishing of the individual as, and I quote, the injurious ones would as a rule predominate over the advantageous ones, end of quote. If you're watching from like the future and I sent you back here, I'm just gonna say that this is something that reminds me of what Malibu in one of her lectures on her critique of Meillassoux Après la finitude, which she calls monstrous becomings. So if you're here from the future, this is kind of like something that speaks to that world. And not to go too far into a tangent, I just think that like what for me is really interesting is when you can kind of see people talking about the same things in different domains. So I talk a lot about patterns, but what I would like to highlight here is schematic structures. So how a structure or a way of thinking is built in one domain by a specific thinker, and then you go to a completely different domain. And this is like something that I really learned from Schrödinger, which is how it is that he's able to learn more about biology through using the structures that he has discovered or studied or learned or perfected or whatever you want to call it in physics. It's much more about you see a structure in physics and you see a structure in biology and you want to see how they, work with one another. You're not trying to reduce one to the other, but you just want to compare so that you can learn more about your structure and more about the other structure. This is one of the reasons why this book, besides all this information, has been so fundamental for me in terms of methodology. Not only his capacity to explain to the layperson all these extremely complex concepts. What I've written here is obviously extremely simplified because this is my resume of his book. But honestly, if it interests you, like I definitely recommend the read. But also going back to Malibu and Meillassoux and this idea of monstrous becomings, it is just much more about you see how concepts or ideas and structures are built in this domain of this dude who, is now in between biology and physics, but he doesn't claim to be a biologist. He's just learned in that field. And he also admits the limits of physics and seeing how it is that we may be able to really think about contingency and laws and necessities in terms of après la finitude or what is discussed in it and the critiques on it. So yeah, I'm going to ferme that parenthèse and we're going to continue with this begs the question what it is that ultimately causes a recessive tendency to become dominant. So what is it that actually causes this change or this jump? A quantum jump is the transition from one relatively stable molecular configuration to another. Similar to the necessity of mutation being a rare event, the author describes the molecule's will of necessity to be of a certain stability where the, and I quote, configuration cannot change unless at least the energy difference necessary to lift it to the next higher level is supplied from the outside, end of quote. A molecule is isomeric when the same group of atoms unite to form a molecule. This is, again, similar to how a chromosome fiber is usually a pair formed between two homologous chromosomes. However, this tendency of configuration as a rule remains open to exceptions, i.e. different configurations. What prevents these exceptions from becoming the rule is that the free passage between two levels or two states of configuration is obstructed. This obstruction is observed by the energy threshold formula in the case of the isomer molecule and the mutability formula in the case of the chromosome fiber, both of which determine the lift needed to arrive at the threshold to disclose relevant change, i.e. quantum jump or mutation. So we have two formulas, and I didn't write this. One, which is the energy threshold formula in terms of physics, and this is the parallel that he makes with the mutability formula in biology. So when we say relevant change, the idea here and something I could have added was that it needs to be a change that maintains itself enough. So the configuration needs to have enough stability to stay in this form for a long enough period of time so that we can recognize this change. Because if it changes and then it just disappears, you wouldn't have noticed the change, and therefore, because we didn't see this change manifest, we're like, there was no change. As mentioned, molecules behave and function in relation to its rivaling tendencies, specifically in relation to heat motion. The influence of heat motion is the small variation in the behavior of small portions of molecules. However, it is when the heat motion becomes significant that it occurs the next level that corresponds to a relevant change of configuration in the isomer molecule. Said differently, variations due to heat motion is insufficient to incur a quantum jump, but a heat bath, which brings the molecule into an environment of high enough temperature to reach the energy threshold between the two levels, is what occurs the transition from one stable configuration to another. Similarly, tests on the mutability formula on the Drosophila fly concludes, and I quote, a considerable increase of mutability with temperature, end of quote. However, these experiments are to be supplemented with a report from Timofeyev. I'll write his name here. Everyone can try to pronounce it with me. Timofeyev's investigations on the laws that govern mutation rates, which conclude that, and I quote, mutation is thus not an accumulated effect brought about by consecutive small portions of radiation reinforcing each other. It must consist in some single event occurring in one chromosome during irradiation. So irradiation is the use of high energy radiation like X-rays. In other words, what we observe in both quantum jump and mutation is the requirement of a consequential level of lift to overcome the obstruction to its transition, resulting in the manifestation of only the radical difference between two levels or two states of relative stability without any recognizable intermediary, i.e. variation or gradation between them. It is in this way that we arrive at the chromosome fiber as aperiodic and crystalline in nature. By locating the locus and the recessive nature of the mutant gene, we have identified its permanence that remains in the hereditary treasure that does not manifest in a given interval but in the right conditions, i.e. the hereditary mechanism. So this is the whole point that I'm actually making this gateway drug of a video. My next two videos is going to be on Schrödinger's, well, the first one is going to be Schrödinger on the theory of evolution, and the second is going to be Schrödinger's speculation of evolution. It has to do with hereditary. It has to do how it is that we actually transmit things from one generation to another. So I'm closing this parenthèse. As it manifests discontinuously, it is considered aperiodic. We have also seen how the change in the hereditary treasure, chemical change of a mutation where chromosomes undergo a rearrangement through crossing over, correlates to the change in phenotype, physical change. It is in this way that chromosome fiber is deemed to behave similar to a solid crystal. For if it was gaseous or liquid in nature, physical change, unlike the chemical change of a quantum jump where molecules undergo a rearrangement, would be observable without any discontinuity. The multiple parallels made, bridged over by the contributions of chemistry, as well as being attentive to the specificity of behavior and functions of the living cell, is how we arrive at the chromosome fiber as an object of physics in the form of an aperiodic crystal. The remaining two chapters examine the extension of a living cell that is the living system. Through the concept of entropy, the author demonstrates how we are to understand the organism as a statistical phenomenon. The fundamental statistical laws of physics have shown us the natural tendency of things to approach a chaotic state, i.e. the rare but eventual event of a quantum jump or mutation. Again, like if you read or if you want to read, I definitely recommend After Finitude, Après la Finitude by Meillassoux. Just the idea of what he introduced as chaos. But it's interesting. I think it's super interesting. However, as, and I quote, life seems orderly and lawful, end of quote, what remains to be answered is, how is it that an existing order is nonetheless maintained? The author introduces, and I quote, two ways of producing orderliness, end of quote. The first being through a statistical mechanism where the physicist produces order from disorder, and the second is through dynamical mechanism where the physicist produces order from order. Refinement in approaching the problem of life, therefore, as Planck puts it, is a matter of attitude. The living cell is approached as a dynamical phenomenon as it adheres to the dynamical laws that govern small-scale events, i.e. the rival tendencies affecting molecules and rival versions of an allele. On the other hand, the living system is approached as a statistical phenomenon as it adheres to statistical laws that govern large-scale events, i.e. the organism with its interactions with its environment. Said differently, we're able to arrive at order from order in the case of the living cell as we identify the threshold order that obstructs multiple and simultaneous mutations, i.e. disorder. However, in the living system, we are able to arrive at order. By the way, living system is just your organism, like your body. We are able to arrive at order from disorder as we take into account entropy, which the author describes as, and I quote, The all-embracing law of entropy increase could be understood without a special assumption of ad hoc, for it is nothing but molecular disorder itself. End of quote. The introduction of these two mechanisms of interpreting life through the ordinary laws of physics is to serve both as a contrast and complement to the picture of the living cell. Firstly, the living system as a phenomenon contrasts that of a living cell in that the living system retains a measure of order or stability in a state of low entropy through its metabolism. The organism avoids maximum entropy, i.e. highest level of disorder or state of death, by exchanging its positive entropy, i.e. friction or, and I quote, all the entropy it cannot help while alive. So existing in general causes friction, which is how he describes positive entropy, with negative entropy from its environment through eating, breathing, drinking, and assimilating. In other words, while the living cell maintains order due to its rare tendency to go through a chemical change, the living system maintains order through constant change, an exchange of positive and negative entropy with its environment. Secondly, this introduction complements the picture of the living cell as it demonstrates how both laws, dynamical and statistical, are not at odds with one another when it comes to observing all phenomena in life, as the dynamical laws that govern the very small are exactly what constitutes the statistical laws that govern the very big. And I quote, "For it must not be believed that the driving mechanism really does away with the statistical nature of the process." End of quote. In other words, from small to big, we are studying the increasingly complex mechanisms that add up to the single phenomenon that is living matter. To conclude, the physicist contributes to the problem of life through two distinct but inseparable mechanisms of identifying or producing order. The first is by identifying the threshold that explains the stability between two states and thus the order observed in the living dynamical phenomenon, cell. The second is by taking into account the point of maximum entropy which the living statistical phenomenon, organism, avoids to maintain its orderliness. The author makes clear, however, that the living matter, and I quote, cannot be reduced to the ordinary laws of physics. End of quote. And this is not in my paper, but essentially this shows how he himself, let's not speculate past what it is that physics can actually tell us, but also I feel like it's an invitation to a pluridisciplinary study of the one thing. So before we had the living cell just as an object of biology, the chromosome, and then now it's an aperiodic crystal, which is an object of physics, and then, the idea of like how multiple domains can look at the same object but with different attitudes, which is something that I find really interesting. So I can see now why he probably thinks I didn't really go into enough detail. And this professor, he's really, really great. He taught us like things that were very, very complex without any notes. This guy had it all in his brain, and he was very scientific, but he was also very, rigorous. So it was a really interesting experience because, the great thing about the uni that we have is that, it's not all just like philosophers like circle jerking, being like, yeah, we're great, you're great, like, you're great. It's like kind of like the physicists and the scientists going like, okay. And this is my weird tangent to going into why it is that I find the next two videos possibly extremely interesting, is that we will actually be talking about something from Mind and Matter, something that he said that this specific professor was like, yeah, you guys can read the second bit. I kind of really don't think that it's that important. So as in What is Life, what Schrödinger wrote in What is Life, he accepts it and he takes it as really helpful and, scientifically backed. But then in Mind and Matter, it's just kind of like, okay. But what we're going to do here is we're going to examine both because I like him as a thinker all around. With quantum mechanics, I am definitely getting a lot of help to try to get more and more understanding. Thank you, Quentin, as well. And if you want to read the full paper and support my work, it is available on my Gumroad, which I will link down below. The reason why I mentioned Malibu and Miyasu is because they are the two authors that we'll be studying in book club. We're currently on Malibu's The Future of Hegel. I don't know how long we're going to be on it, but I think it's worth going through slowly because it's a very dense read. And the same with Après la finitude. But honestly, if you're going to read two books the rest of this year, definitely recommend What is Life and Miyasu's Après la finitude. I hope you found this helpful, and I hope you enjoy the things that I pulled out in terms of Schrödinger's speculation on evolution. I hope you have a great day. I'll talk to you soon.